This is EC 201 lecture 29. So the last time around we moved on from the NMOS and the PMOS transistors to another family of active devices called the bipolar junction transistors. Specifically, we considered an NPN transistor whose terminals are called the collector, the base and the emitter. This is the collector current IC, and we also found that there is a new effect in that the base current, unlike in a MOSFET where the gate current was 0, the base current here is not quite 0. It is a small fraction of the collector current, and the collector current is the effect and is given by Is exponential VBE by VT. And for those of you who didn't show up on Saturday or left in the middle, VT now is not to be confused with the threshold voltage of the MOSFET. In the context of a bipolar transistor, it stands for the thermal voltage KT by Q, about 25 millivolts at room temperature. Okay. This expression is valid only when VCE of the device is greater than some VCE SAT, and VCE SAT is about 0.65 volts. And another thing, observation that we made was that the collector current of the bipolar transistor increases so rapidly with VBE that you can turn the argument upside down and quite safely say that if a reasonable collector current is flowing, where reasonable is defined as big, small, reasonable, non-reasonable, these are all relative terms, must be quantified with respect to something. So if I said that a reasonable amount of collector current is flowing, then the base emitter voltage is approximately equal to around 0.65 volts. So now the question is, what is a reasonable amount of? So a reasonable amount of collector current basically means something which is much larger than the reverse saturation current Is. In other words, you can see that VBE is given by VT ln of IC by Is. So as long as the argument of the logarithm is reasonably large, maybe 100 or 150 or 200, whatever, you know that the logarithm is a very weak function of the argument. So as long as this quantity here is sufficiently large, you can kind of, if you look at the curve, you see that it's rising very slowly, and such amounts of current are not at all difficult to achieve and are used all the time in practice. Is is of the order of a few picoamps. So, normal currents in the case of bipolar transistors would at least be several hundreds of microamps. So we can see that this IC by S is a large number, and it turns out that, loosely speaking, if you say that a reasonable amount of collector current is flowing in the transistor, it means that you can approximate the base emitter voltage of the transistor by a nominal value given by about 0.65 volts. Now nobody is going to shoot you if you use 0.7 volts instead of 0.65 volts, or 0.6 volts instead of 0.65 volts. Okay, this is just a nominal value that one can use, or one won't be making too great a mistake if one blindly closed his eyes and said, oh, if the collector current is flowing, that means the base emitter voltage is approximately 0.65 volts. As we saw the last time around, the IC versus VCE characteristics of the transistor very much resemble the characteristics you saw in the MOS case, that is for different values of VBE. If you plot IC, you will find that you will get characteristics of this form. What is this voltage? VCE SAT, which is 0.65 volts. These curves are drawn for different values of VBE. Can you comment on the base current in the transistor for different values of VBE corresponding to these three different curves? the base current will be increasing. Why? It's IC by beta. So VA1 must be smaller than VA2 and must be smaller than VA3, which means that the base current in this case, when the applied base emitter voltage is VA1, should be smaller than the base current when VA2 is applied, which should be smaller than the base current when VA3 is applied. Does it make sense? And traditionally, while there is absolutely nothing wrong with drawing these characteristics for different values of VBE, do you guys foresee any practical problem while plotting? If I gave you a bipolar transistor and said, hey, go and plot me the characteristics of IC versus VCE for different values of VBE, do you see any practical problem? So the IC is an exponential function of VBE, so what is the problem? Since the bipolar transistor is so sensitive to the VBE applied, in practice, it becomes kind of difficult to apply a VBE and plot the collector current. So what do you suggest? So what is normally done, traditionally done while measuring bipolar characteristics is the following. This is VCC. You put an ammeter here. Instead of applying a VBE, what people do is put a large resistor in the base like this, and what would be the base current? If RB is very large, the current here is accurately VCC minus VBE by RB. So IB is nothing but VCC minus VBE by RB. And what do we know about VBE? VBE is approximately 0.65 volts, which means that IB is approximately VCC minus 0.65 volts divided by RB. This is IB. What will IC be? In the active region will be beta times IB. So, and how will you vary the base current? You want to see different collector currents, so you want to see different base currents. So you will vary RB, and as you vary RB, the base current will change, which will also change the collector current. So you will take readings by varying RB. I mean, you would have naively thought that you could change the VBE, measure IC. I mean, the collector current is an exponential function of VBE, whereas it's only a linear function of IB. When you look at bipolar transistor data sheets, you will always find that the IC versus VCE characteristics are not plotted with varying VBE, but they are plotted with varying IB. Fundamentally, there is no problem. You could have actually done it with varying VBE. So, IC VCE characteristics are plotted for various values of IB. Whereas when you have a MOSFET, the ID versus VDS characteristics are plotted for various values of VGS. Okay, and the legitimate question, the whole reason behind going into this discussion is that a legitimate question would be, when you pick up a bipolar transistor data sheet, why are the curves shown as for different values of IB, whereas the MOS transistor they are shown for VGS, and this is the reason. Does that make sense? Alright. And the last time around we also saw, once you have the equations for the nonlinear device, it's quite straightforward to come up with a small signal equivalent model. And what did we say the small signal equivalent model was? We had, this is the this is the collector, this is the emitter. What is the value of This resistance here, this is beta Vt by IC, where IC is the quiescent current flowing through the collector. This is a current controlled current source of value Gm times VBE, where VBE is the incremental voltage between the base and the emitter, and this is an output resistance which is of the form VA by IC, and VA is called the early voltage. And what is the value of Gm itself? It's IC by Vt and is obtained by differentiating the relation between the collector current and the base emitter voltage. You can see that unlike in a MOS transistor where the expressions are quite complex, in a bipolar transistor, once the bias current is known, transconductance is determined in a very straightforward manner. It's just IC by Vt. So this is all review of what happened the last time. The next thing is, once we have a device, the next thing is we started making our amplifiers. And how did we make our amplifiers? We said, here again, all we are doing is biasing the transistor with some VBE, and as we just discussed, this is a terrible thing to do because the collector current is a very, very, very sensitive function of VBE. So a small error in either RB or RA or both can cause a dramatic change in the IC. So that's clearly not an acceptable solution. So you should never bias a bipolar transistor this way. In other words, we want something which is robust. Just like in the MOS case, we wanted the bias current to be insensitive to the threshold voltage of the device and all this other stuff. So what we do is the following. We can do what we did for the MOS case. What did we do in the MOS transistor case? We apply negative feedback. The first thing is to compare. In the MOS case, we compared the drain current with the reference current and go and kick the gate. Here, you should replace drain by collector, you should replace gate by, you compare the collector current with the reference current and go and kick the base. If you have another identical transistor, what you can do is to use the same base emitter voltage and connect this to this is VCC, this is RC, and just like what we did with the MOS transistor, you could do this. You could add on the infinite capacitor and the input this way, and the output is taken at the collector. And the incremental gain is basically minus Gm times RC. This guy here is the bipolar version of the current mirror that we have seen in the MOS case. No big deal. The next thing is to say, if I didn't have to use two different transistors, we can still do what we did in the MOS example, which is what? Put a large resistor between the collector and the base. Let me call this RB. This operates on the same principle. However, with this, there is a definite disadvantage when compared to the MOS example. Can you think about it and tell me what it is, what the problem is? One is, of course, that once you have bipolar transistors, base current will flow. The actual collector current will be slightly smaller than IREF by the base current. And since the base current is very small, it's typically about 1% of the collector current, perhaps it's not a big deal. Do you see a fundamental problem with this arrangement? Think about swings. In an NMOS transistor, the drain can go one threshold voltage below the gate and the transistor will still be in the saturation region where it gives you gain. In the bipolar transistor, VCE minimum is 0.65 volts, VBE is, what is VCE sat? 0.65 volts. What is VBE nominal? 0.65 volts, which means how much I left to, how low can the collector go? This is approximately 0.65 volts, VBE nominal. If this goes below 0.65 volts, then you are in trouble, which means, what can you make any comment about the difference between, analogous to the mass case, how low below the base can the collector go? 0. So the collector cannot go below the base. Okay, if it does that, then you will enter the saturation region in the bipolar transistor, which is not where you want to operate. The transistor behaves like an active device only if VCE is greater than 0.65 volts. Does this make sense? Okay? In an NMOS transistor, the drain can go one threshold below the gate. In an NPN bipolar transistor, the lowest the collector can go is the base voltage itself. Okay, so now based on this new observation, can you comment on the usefulness of this bias technique? Assume that the base current is very small. So can you comment on the quiescent potential at the collector versus the quiescent potential at the base? They're almost the same. Okay, the only difference between the collector potential and the base potential is that is this IB times RB. If IB is very small, which is what you will get for a good bipolar transistor, then the quiescent potential at the collector is the same as the quiescent potential at the base, which means that while the transistor is biased okay, alright, this is hardly of any use because the moment the collector starts to swing, the transistor gets into the saturation. Does that make sense? So this is of, as I said, this is of limited usefulness. What is the next bias technique that we saw in the MOS case? The next bias technique was to measure the source current and tweak the source node. So the corresponding bipolar equivalent will be to measure the bias of the base at some fixed value, compare the emitter current with the reference current and go and kick the emitter itself, and that leads us to this bias technique. And now if you wanted to make a common emitter amplifier out of this, what would you do? We do what we're used to, which is RA, RB, that's used to generate the bias voltage at the base. You have the load resistance RL. You have VCC. This is IRF. So this biases up the transistor. What is the quiescent voltage here? Be a little careful now. Let me call that quiescent voltage VB. Can you estimate what VB will be? Do you need to know anything about the transistor or you don't? I need to know IB. Okay, so let us assume that we somehow figured out IB. So VB will be VCC times RA by RA plus RB. Will it be greater than this value or smaller than this value? Smaller than this by you have IB flowing here, you have VCC here, you do it one at a time. So if IB wasn't there, this voltage would be VCC times RA by RA plus RB. If VCC weren't there, what will that voltage be? It will be minus IB times RA parallel RB. Some potential at the base will be influenced by the base current. I mean, now you don't want to keep going calculating base currents and, finding RA and RB. I mean, you want VB to be something. You hardly want to spend the time trying to figure out what RA and RB should be by going and calculating, finding beta and base current and all this other stuff. What is a quick and dirty way of making sure that the quiescent voltage is approximately what you want? One way of making VB approximately equal to this guy is to make IB times RA parallel RB much smaller than VCC times RA by RA plus RB. Equivalently, can you think of a common sense way of expressing this? If there is a big stream of water flowing, when will nobody notice if you steal a little bit of water? When will this potential remain VCC times RA by RA plus RB? If this current flowing here is between VCC and through RA and RB is very large compared to this current, then this node will hardly notice that any current is flowing off, and that the node potential will be approximately RA by RA plus RB. Does it make sense? So you want to make sure that a torrent of current flows between RB and RA, and a small base current is lost. This potential will remain quite accurately VCC times RA by RA plus RB, so you don't have to break your head by calculating beta and finding beta and IB and all this other stuff. So the design consideration for choosing RA and RB is to make VCC by RA plus RB much greater than IB. Is that clear? In the MOS case, you could choose the RA and RB arbitrarily. You only were interested in VB, and the VB won't be influenced by the MOSFET at all. Now in a bipolar transistor case, you can't do things arbitrarily. Ideally, you want to choose RA and RB to be very high or very small. As far as the input signal is concerned, which you will add like this, do you want RA and RB to be large or small? We want RA and RB to be large because RA parallel RB will appear in series with the source impedance. But if I go on choosing RA and RB to be larger and larger, what will happen is that the base voltage, the quiescent voltage at the base will go on reducing below the value of VCC times RA by RA plus RB. There is an upper limit to RA and RB. Does that make sense? So that's the quiescent potential at the base. And if we have done a clean job of design, VB will be approximately VCC times RA by RA plus RB. What will be the quiescent potential at the collector? The quiescent current through the transistor is please note that this is IB, this is beta IB. IC is beta times IB. I can write that equivalently as IB, which is IC by beta, which means that IC is what? IC plus IB must be equal to IE. So IC plus IB must be equal to the emitter current, which is equal to IREF, and IC by beta is IB, which implies IC is beta by beta plus 1 times IREF. So this quantity beta by beta plus 1 is often denoted in the bipolar literature by this number alpha, and if beta is large, alpha will be close to 1. I will make the assumption that beta is large here so that IC is approximately equal to IE, and that should be equal to IREF. So what will be the quiescent potential at the collector? VCC minus, that's the quiescent potential at this node. So are we done with our common emitter amplifier, or is there some serious problem? Just like in the case of the common source amplifier, you must incrementally ground the source. Here you must incrementally ground the emitter. So I am not yet done. I must put an infinite capacitor here. So if I want to now draw the small signal equivalent, so what will be the equivalent circuit of VCC? Incrementally ground. What about the capacitor, the infinite capacitors here and here? They will be short, the current source will be an open, so I can get rid of these guys. And you have to replace the transistor by its incremental equivalent circuit. And what is the incremental equivalent circuit? The emitter was grounded, mind you. This is RO. This is, if this was Vx, this will be GM Vx. And what is the value of this resistor? Beta by GM, or beta Vt by I. So what is the incremental voltage Vx in terms of Vs? It is Vs times, it is beta by GM parallel RA parallel RB divided by RS plus beta by GM parallel RA parallel RB. What is V out in terms of Vx? Minus GM Vx times RO parallel RL, which means that the incremental gain V out by Vs is of the form minus GM RO parallel RL divided by RS plus beta by GM parallel RA parallel RB times beta by GM parallel RA parallel RB. Does it make sense? And how will you evaluate the swing limits? When do you define the transistor cut off? IC is 0, which basically means that you have to find the total current. The total quiescent current, assuming beta is large, the collector current is approximately IREF plus GM times Vx. This is the total collector current. This is the quiescent part. This is the incremental part. And Vx is directly proportional to Vs, so you can go and figure out what the stuff is. Limit for the BJT getting into the edge of the saturation region. How will you figure this out? VCE is equal to VCE sat, which is equal to 0.65 volts. Okay. Or VB is equal to VC. VCE being equal to 0.65 volts is equivalent to saying VB equal to VC. It's pretty straightforward, right? We cancel out the E's on both sides. Huh? And what is VB? The base, the total potential at the base is of the form, the base voltage is nothing but VCC times RA by RA plus RB, assuming that we have chosen RA and RB wisely, plus the incremental value, which is simply Vx. And the collector voltage VCC minus IRF RL, this is a quiescent value, minus GM Vx times, GM RO parallel RL times Vx. And from these two you should be able to, what did we say when we were discussing the common source amplifier where we had this current source in the source? We said that in many practical situations, especially in discrete circuit design, it's not possible to get current sources. So what do? What's a poor man's current source? A large resistor. So this is now a very commonly used bipolar technique. I'm not going to go through how we jumped from the current source to the resistor all over again. It's the same reasoning. This is VCC, this is RB, this is RA, this is R, let me call this E for emitter, and this is RA. So two issues need to be addressed. What are the two issues that need to be addressed? We know that the RE should be a large resistor. The obvious question is, how large is large? What do you mean by a large RE? The other thing that's of relevance is other information that we'd be interested in finding. The first thing what we'd be interested in is finding the quiescent current. Correct? In fact, this RE is secondary. First thing is to find what the quiescent current is. So I will move this lower in the order of importance. So how will you find the quiescent current? Let's assume beta is infinity for the time being, so there is no base current. How will you find the quiescent current? Apply Kirchhoff's law. One thing you can be absolutely sure of in this subject, there is nothing more basic than Kirchhoff's voltage law and Kirchhoff's current law. That will never fail. If beta is infinite, what can I say about the collector current and the emitter current? They are the same if beta is infinite. So I will call that equal to IC if you like. So now help me write Kirchhoff's laws. What is VB? VB is nothing but VCC times RA by RA plus RB, and this must be equal to this voltage, the base voltage potential here must be equal to this potential plus the drop across RE. Correct? And what is the drop across RE? Must be equal to IC times RE plus VBE. And what is VBE? VT ln IC by IS. This is the completely legal Kirchhoff voltage law. There is no approximation here at all. And as we've seen with respect to nonlinear circuits before, computing the operating point, could involve nonlinear equations, and this is one example of such an equation. This is an implicit equation in IC. In the MOS case, what did you get? When you were doing the MOS example, we got square root, okay, because that's the inverse of the square law characteristic. Now, we are getting a log because it's the inverse of the exponential characteristic. With the square root, you can solve the quadratic and find the voltage. Here you can take an easier way out, which is why I like the bipolar so much. You say that this is approximately equal to VBE nominal, which is equal to 0.65 volts, which means that IC is approximately given by VB minus 0.65 volts divided by RE. Does that make sense? Is this an exact expression or is this an approximation? This is an approximation. So there must be some terms and conditions associated with the making the approximation. When do you think this approximation will become more and more accurate? VB is ICRE plus VT ln IC by IS, which is VBE nominal plus some error. The moment you assume that the base emitter voltage is VBE nominal, it means that the true base emitter voltage is not quite what you've assumed, but there is some error associated with it. So when will the IC you compute using only this part of the equation be close to the true IC? When the error is very, very small. And that is very easily satisfied provided this is a constant. If this potential is much, much larger than this guy, then any error you make here will hardly reflect in ICRE. Does that make sense? So you want to make sure that this ICRE is very, very large. So one simple way of ensuring that the approximation is valid is to make sure that ICRE is much, much larger than VBE nominal. This is one sure shot way of making sure that the error is very small, because the error will be a small fraction of this, of VBE nominal itself. Okay? If this guy is much larger than these two, then you make almost no error, which is equivalent to saying that if this guy is much larger than VBE nominal, you definitely make no error at all. You understand? The quiescent current is quite accurately given by VB minus 0.65 volts divided by RE. So I think that's a good break point. So